Let me start thanking Hardy and Carlos and Christian for letting me speak about my work. Okay, so I will start with some motivation and background. So first of all, we are interested in spectroscopy and in particular in photoemission. Okay, so you have a direct photoemission in which you would remove an electron from your system, and then you have inverse photoemission in which you can add an electron to your system. And in doing this, you have information about the electronic structure of your system, so the quasi-particle band structure, but also about other excitations of your system, such as neutral excitations. So I'll speak about this a little bit later. So in general, the state-of-the-art method to describe photoemission, in particular in solids, which is our target here, is many-body perturbation theory based on the one-body Green's function. Okay, so the one-body Green's function, you don't see my pointer, right? Okay, doesn't matter. The one-body Green's function describes precisely the propagation of a quasi-particle in a system, and it's actually strictly linked to the one RDM because you see the Green's function depends on a time difference at equilibrium, and so the equal time limit gives you back the one RDM. However, when you do this, a lot of information are lost because you see, thanks to this time difference in the Green's function, when you go to Fourier space, or you go to frequency space, you see that the Green's function has some poles precisely at the addition and removal energy of your system. So here, what you see here in the denominator are total energy differences. Okay, so these are precisely what we measure in photoemission. And then you have some weights that are usually called Feynman amplitude or Dyson orbitals. Okay, and so then you can get the spectral function from the imaginary part of G. So you have a series of peaks with some weights. So a typical sketch of a spectral function is here on the left. If you don't have interaction in your system, you have just delta peaks, which represent the energy of the quasi-particle. And when you switch on the interaction, then this quasi-particle has some broadening and other peaks appears. And this is because when you look at the photoemission process, here on the right, I sketched the case of removal energy, so direct photoemission. You remove a particle and the whole left in the system can excite the system. So you can see the photoemission, direct photoemission as at least a three-particle process, okay? So keep this in mind because we will come back to this later. Okay, of course, then you need a practical way to calculate the 1GF, and this is through this Dyson equation, in which G0 is the non-interacting G, and all the correlation part is hidden in sigma. So here, sigma plays the role of the constant potential within the FT. Okay, so you need to find approximation to these self-energies, and a well-known, in particular in solids, very used in solids, is the GW approximation here on the left. So you have the R3 contribution, and then you have this GW. W is the dynamically screened Coulomb potential, which makes physically sense. When you have an electron system, the interaction between electrons is not just the bare Coulomb interaction, but it's screened by the presence of the other electron, so it's much weaker. So just to keep contact with the more known theories like R3-Fock, when W, so when there's no screening in your system, W is V, and that is the exchange. Okay, or if W is static, then you have the screen exchange, right? Okay, so why then, I mean, I speak in my title about EKT, why don't we simply use the many-body perturbation theory to calculate photoemission? Well, because there are some limitations. And here I start with a simple case of the Hubbard dimer. Okay, so here you have just one level per site, and the interaction is local, and you have some open parameter T which is related to the kinetic energy of your system. So changing the ratio U over T, you can explore different range of correlation. So on the left-hand side, you see U equal 4, T equal 1 is a moderately correlated system. You have the exact solution, 2 quasi-particle peaks to satellites, and GW doesn't describe so well the satellites. The quasi-particle band gap, you see, is slightly smaller than the exact one. And then the screen particle parallelity matrix is another more advanced approximation, which anyway, you see the band gap is a little bit underestimated. The worst happen when you go to the atomic limit. So the atomic limit is when you stretch your dimer. So then the 2 electrons, they localize each on one side with equal probability. So this is the regime that we call of strong correlation. And you see that here all these approximations fail because you don't have a band gap. So you have just one peak in the middle of the gap. So this is this physics is not just of the Hubbard dimer. It's also found in real materials. And a typical strongly correlated material is nickel oxide in the paramagnetic phase. Okay, so here this system, just to sketch it, you see you have nickel, the nickel atom has 8 electrons. Due to the crystal field, you have some splitting between of these the electrons in T2G and EG, and EG are partially occupied, and that's why this standard theory, standard approximation give you a metal, while in nature it's a insulator, and it's precisely the interaction of the strong interaction of electrons in the EG which opens a gap. Okay, so this is a challenge, and there is a lot of work in many-body perturbation theory to try to describe these systems. And that's why about more than 5 years ago, we started to look for alternative way to describe photoemission. And here now started the true talk. So this is the outline. I'll have a look, we'll review with you the basic equation of the EKT. We will see how the equation reduce in RDMFT, and then I will suggest some modification to the original EKT equation in order to capture strong correlation. So let's start from the removal energies. Okay, so here, this is the definition of the removal energy, total energy differences. Okay, so far everything is exact. And then in the EKT, we do an ansatz for this many-body wave function of the n-1 electron system. Okay, so it's some linear combination of distraction operators acting on the ground state wave function of the n-electron system. So if you introduce this ansatz, okay, you can do some manipulation. You arrive at this expression in terms of this commutator. Sorry, like you cannot see my pointer. Anyway, right, and then what you can do, you apply the stationary condition with respect to the coefficient C, which enters in the O operator. And when you do this, you end up with a generalized eigenvalue problem in which the ingredients are in terms of this commutator with the Hamiltonian and the density matrix. So in principle, this can be used in any framework which can provide you with these two ingredients. Okay, so before passing to the RDMFT framework, let's see what is the physical meaning of this EKT. So usually you find that this is the explanation of this ansatz. So essentially it's based on this quasi-particle like ansatz. Okay, so you have your many-body wave function, you remove an electron, and the rest of the orbitals are not relaxed. Okay, however, since we are interested in spectroscopy, it's nice to give another point of view, so to give an interpretation of these energies that we can calculate. So if you take the removal energy, so this is the expression that you get once you use this quasi-particle ansatz, okay? So you see here, you have a commutator between the operator O and H. So you can work out this commutator and let H act on left and right on your wave functions, okay? That's why you end up with some total energy differences. And this total energy difference is precisely the definition of removal energy. Okay, and the rest in the expression are just the weights, are the Dyson orbitals, essentially are the weights of the Green's function, the removal part of the Green's function. So the last expression, so what does this say? So since we are working in a basis set, for each component I, okay, of your removal part of the Green's function, you will have several peaks. Okay, well, the EKT gives you a weighted average of these peaks. So, for example, if you have here, for an I component of G removal, you have all these 4 peaks, the EKT gives you this weighted average. Okay. All right, so going back here, so now if you want to use it within RDMFT, we can work with the natural orbitals, and we can work out the commutator in V, and one ends up with this matrix, the lambda matrix, which is just in terms of the Coulomb potential and the non-interacting part of the Hamiltonian, and the two-body density matrix gamma 2. Okay, you can diagonalize it and you get the removal energies. You can do the same, so the whole procedure can be done also for the addition part of the spectrum with a similar quasi-particle ansatz for the EKT, and you end up with this other equation to diagonalize and you get this. Okay, so usually the EKT is used mainly for removal and addition for the energies. Okay, but in photoemission spectra, if you want to describe the spectra, we also need the weights. Okay, so one can easily generalize this to a spectral function, and the spectral function has this form here. So you see, you have a series of peaks and the removal addition energy calculated with the EKT, weighted by this diagonal part of the, in this case, removal part density matrix in the basis which diagonalize lambda R or lambda A, which is not necessarily the same basis. Okay, so now you can already start to understand that if you have a spectral function, an exact one, well, the spectral function of the RDMF of the EKT will tend in general by construction to overestimate the band gap, precisely for the interpretation of the removal addition energies that we have given before. All right, so let's see how all this works. So let me just spend a few words on how we use the whole protocol. So we just use RDMFT. We have the total energy with some approximation. So the approximation that I will show you are the power function, which was introduced also by Hardy, okay, which is this factorization of the exchange correlation part of gamma 2 in terms of this 1 RDM with this parameter alpha, and you can change it between 0, 5, and 1. You can get the Mueller 0.5 or Darty-Fock when alpha is 1, okay, which means simply that you put this alpha in the eigenvalues of gamma 1. And then we use this, so this is optimized, we get the optimal natural orbital set occupation numbers, and we built the EKT equations, in which also the gamma 2, which appears in the EKT equation, is approximated with the power function. All right. Okay, so when we do this, we start again from some models. So this is the case of the 6-site Hubbard ring. Again, you have the exact solution. You have the EKT using exact ingredients. So you see it works pretty well also at t = 1. And you see at t = 0, so in the strongly correlated limit is exact. And this is because you have just one peak. You see in the exact solution, you have one peak per component of your corresponding G1. Okay, so the weighted average is just the peak, the quasi-particle peak, if you want. Okay, that's why it's exact in this limit. Then if we go away from 1/2 filling on the right-hand side, also it doesn't work so bad, but at t = 0, you see some band gap appearing where there should not be band gaps, which suggests that in metals, the EKT might open an artificial gap. Okay, so we will see this later with homogeneous electron gas. Then some more info about the band gap when we increase the number of sites. So again, in black, you have the exact band gap, okay? In blue, you have the EKT band gaps obtained with exact ingredients. So you see the overestimation that I told you. It's exact only for the Hubbard dimer because of the limit number of peaks in the spectral function. So the weighted average is not an approximation. And then it overestimates the band gap. And then, of course, you can play with, here we use the power function. You can play with alpha to get a good band gap, but this is just based on cancellation of errors, okay? Then we go to the homogeneous electron gas. So here the black are QMC results, and in green, so we didn't have QMC ingredients for the conduction part. So we have just the valence part in green. So EKT using QMC ingredients, and you see that there is the bandwidth is slightly wider than the exact one. And then when we use approximations like the power function, this bandwidth is a bit larger. And in particular, you see the opening of an artificial band gap in the EKT, okay, which should not be there. So it tells you that if you use it in metals, also there you have a band gap. So we go to some realistic systems. This is silicon. So this was the whole procedure. The EKT was implemented in the ELK code, and you see that also in this case, of course, here we don't have we have the EKT and the QMC, so it's very difficult here to see what you have to look at, but you see here at the gamma point are the EKT with, let's say, very accurate ingredients, and you see that indeed the band gap it's a bit overestimated with respect to the experimental one. When you use approximate functional, so in this case the power function, the bandwidth is, so the red points is very huge in the valence part, and the band gap is really hugely overestimated. So this means that when you use approximate functionals, of course, the overestimation of the KT can be much amplified. So how can we now improve over this result? So the first thing that you understand is that we have to improve the approximation to the two body density metrics that are available, which is not easy, right? For solids, really, there's a lack of approximation. Okay, so we tried to change the power function in such a way to introduce, let's say, some correlation, and this is based on the link between the Green's functions and the density matrices, so in particular between gamma 1 and gamma 2 and G1 and G2. Okay, so this means that exploiting this link, you can write this term V gamma 2 in terms of the self-energy. Okay, and what we use here is a GW self-energy within a static approximation, so you end up with the approximation on the right-hand side. For alpha equal 1, you have the spin exchange that I've already explained at the beginning of the talk, but we put alpha different from 1 for the following reason. If you take a static W, you cannot get fractional occupation numbers, okay? So when, let's say, we try here to reintroduce the dynamical dependence on W through the parameter alpha. Alpha will give you fractional occupation numbers. Of course, you can have double counting and all this, as we will see. So how does this perform? So this is the approximation that now we use for gamma 2. And again, silicon. So yeah, here you have to look at the light blue dots now. And well, for the valence part of the bands, for the band structure, you can see that the bandwidth is much improved. So this is nice. And also the conduction bands are shift down. So this is also nice. The problem is that we have bands in the band gap region. Okay, so the gap basically closes. And this is because there's too much correlation in this function. So this was a nice try, but didn't work so well. So then I said, okay, maybe instead of looking for better approximation to the 2RDM, we can go beyond the EKT. And in fact, you can do this because you remember at the beginning I said that the EKT is based on quasi-particle ansatz, okay? But in a photoemission process, there are at least 3 particles involved. So you can introduce in your ansatz also this electron hole excitation that I have depicted here on the left. So you can change your operator O in such a way that together with the destruction of an electron for the removal part, you have also the creation of an electron hole pair, and also and the same in the operator O dagger. Okay, so if you do this was illustrated in this paper by Lee, Malone, and co-workers, the EKT3 equation, they will depend on gamma 3 and gamma 4. Okay, so it becomes extremely heavy. And moreover, there are no practical approximation to gamma 3, gamma 4. Yes, of course, you can factorize them in terms of gamma 1, gamma 2, but we don't have good approximation for gamma 2 either. Okay, so what we said, okay, why don't we try to introduce in an effective way the effect of gamma 3, gamma 4 in the EKT equation. So what's important here? Here, what is important is the screening, right? Which comes from the electron hole pairs. Okay, so we took the EKT equation and we modified in this way. So you see that here, for the removal part, the terms which depends on the exchange correlation part of gamma 2 now has the W, so the screen Coulomb interaction. And also in the addition part, there is a part in which V was substituted by W. So how to justify this? Well, this was done on a pragmatic, in a pragmatic way, I must say. So first of all, we had already shown that if you take a screening like in point 1, okay, well, this kind of screening can describe some of the effects of gamma 2, gamma 3. This was shown for nickel oxide, okay? And you can improve your spectrum. And then this EKT modified screened EKT equation reduced to the screen exchange equation when a system is described by a single slit determinant. So this is, you can show it easily, that they reduce to the screen exchange of many body perturbation theory, when essentially the occupation numbers are 0 and 1, which is the case for weakly or moderately correlated systems. Okay, so let's see how this screen EKT works. So again, I have the case of silicon, and now you have to look at the blue dots, and you see that with the blue dots, the band gap is the bandwidth is very well described, and the band gap is good. We still have a little bit of estimation, but it's very good. Okay, which we can expect because this screen EKT should reduce to screen exchange, which in general works well for silicon. Okay, so let's see a bit the photoemission spectrum now. So we have a bunch of systems here. So the idea was that we want to reproduce the good quality that we have in GW for weakly correlated systems that here are represented by lithium hydride and silicon, and this is generally the case. And then also we want to open a gap in nickel oxide. So here I have the two cases. Paramagnetic case is here NM, non-magnetic, and antiferromagnetic case. So you see that you have a overall good agreement with the experiment. So you have to look at the red curve, and the dashed blue curve is the bare EKT. So it's not all so nice. I mean, in general, it's okay, but you see that there are some stretching of the valence band in nickel oxide, Okay, and moreover, if we look at the composition of these bands, here on the left I have the composition, so the projection over SPD orbitals. On the left, the EKT composition actually is very similar to the composition that usually we have in other methods like DMFT, which are used for strongly correlated systems. But when we do the screen EKT for silicon and lithium hydride, the composition of the bands is still okay. But for a nickel oxide, you have that the SP bands in the band gap region, they go below the D bands for the conduction part. And this is should not be the case. Okay, and this is explained by the fact that, of course, in these systems, you have a very strong difference between orbitals. You have weakly occupied orbitals and strongly occupied orbitals, and the screening acts on them differently. Okay. Okay, so I arrive at my conclusions here. So I propose to modify the EKT, introduces screening, which makes physically sense. This modification seems promising, although some deviation remain. Okay, so improvements are needed. So the idea is to use a better screening. Now the screening, I didn't speak too much about it, is the RPA screening, but one could think of improve it or to use a different screening depending on the kind of orbitals it acts on, if they are weakly occupied or strongly occupied, a little bit like it's done, for example, in the BC functionals for the ground state. And of course, we need a better approximation to do RDM for solids. And this is not so obvious because many advanced approximations, so during the workshop, there was Mario speaking about his function, which are very advanced, but the extension to solids is not always so straightforward. Okay, so we have to think how to do this when you have more than one K point. Okay, so with this, I want to thank the people who work on this. In particular, Stefano Di Sabatino was involved in this research for a very long time, and Jacob Koskelo, who implemented a lot of the EKT in ELK, and my collaborators locally and at the Polytechnic. And I thank you for your attention. And if you have any question, just ask me.